So my name is Stefan Schmidt. I am working at the Oniro project, which is a new working group in Eclipse Foundation. I mean, we're a year old now. Yesterday actually was the first year, our first birthday celebration. And I'm working for Huawei as a principal solution architect, and I work in different parts of the Oniro ecosystem. And one project I'm working with is the Eddy project, and that's what I want to talk a little bit about here today. So I will start with a little bit of an introduction, then describe what are the actual goals we are having with the project, what are use cases we are having. So I will demonstrate one, but there are definitely more that I'm not covering all of them here. I will go into the implementation details we are having. So what is the current status, what we are supporting, what is the next things we are planning. So basically giving you a bit of a roadmap for what's coming up. So let's start with introduction. So Eddy. It's not really a good acronym or anything, but if you want, you can make it up and make it like enabling distributed intelligence. If you push around the characters, you will get Eddy out of it. So as I said before, it's a project in the Oniro working group. It's a cooperation between various companies. So we have inside the working group, we have Synesthesia as a company and Huawei as a company interested in that. And then we have the Politecnico di Milano research at the university in Milan, and they're working with us on the research side of these things. It is a middleware. It's composed of different layers, so nothing new there. It's Apache 2.0 licensed. It's a C++ code based, but we have it. We designed it in a way that it's taking constrained devices in mind. Come to that later, why we do that, but that's important for us, so that's why I want to mention that here. So and then we have like different implementation flavors right now. So we have on Oniro we have flavors for Linux as well as Zephyr as one of our RTOS systems. And that is what we are aiming for at the moment, and that are the use cases and the implementations we're actually working with here. And a word of warning, so this is very much work in progress. I'm not showing you any finished project here that you can take and use or something. This is really something we are working on right now, and as you will see on later in the implementation details, we haven't reached all the layers that we are planning on right now, but at least we wanted to showcase what we are working on, so if others are interested in that, you have a chance to get involved early on. So take that in mind. So what are the goals and the use cases? Why did we go ahead and start that? So it's not really a mission statement, but when we sat down and wondered what we want to solve with Oniro, I mean, one of the key points we're having was like, we're having all these very different devices, and we need to find a way to actually make use of these resources. And that works well for like small use cases. So you have an app on your phone that works with a specific IoT device in your home. Fine. You might even have an ecosystem like from Apple or Google or whatever. So you have it there, and then you work with very many devices and so on. But there's always a limit to all of these things. And what we envisioned was more like that the application and services have a global view across all the devices and have a unified view, a unified pool of these resources available. So that's like one of the big concepts we wanted to achieve here. We are far away from that, but we are on the way to do that. So we set out and said, okay, this is more like a research project, so we partnered up with the university and get some knowledge from the academia out of that, and then try to bring that into implementation, and then really get that into the Oniro project, and maybe at some point productize it. So what we want to have is we want cross-device, but also cross-operating system view on that. So we start with Linux and Zephyr. Right now, we're focusing on normal peripherals and stuff like that. So we are not talking about general purpose resources like CPU or memory. Going into that with all the implications on scheduling and so on is difficult. So we set that aside for a while, but that's definitely something, if we are going forward with the project, that's definitely on the roadmap. Maybe not next year, but maybe after. So this is like one part of it. So we have like, we want to have an understanding of what resources are available around us. That could be a context like for a person in your car, in your home. It could be in a factory or something like that. So it's very generic in that regard. And on top of that, we want to make sure that we make an efficient use of these resources. We want to make sure that we can orchestrate our workloads or our needs, our use cases based on the available resources. So, and one of the key points here is that with having this view of the resources and making it available, it would be like instantly compatible to your local applications. That could be your camera application on your phone that is not only using the camera that you have on the phone directly, but maybe the security camera that is sitting in your house, or your doorbell camera, or a dashboard camera on your car, or something like that. So these are things that it would express itself as another camera device, and then the application would just see that and you can switch over. Or even have like the intelligence part kicking in and like it deciding to move to a different camera based on your patterns and so on. Yeah, so the thing is we have all these resources available, but selecting them manually and making the right decision and so on can be very overwhelming. So we want to have like orchestration kicking in here and trying to make that better. And at that point, we will most likely switch away from having a very basic rule set engine where we define the rules or the user defines the rules and going into a more complex orchestration where AI might be an interesting part to handle parts of these. So, example. I touched on the video capabilities before. So, think about that. You go and you want to finish off work early because you want to see a family, so you take the last video call on your commute back home. You start the call on your mobile when you're leaving the office, and then you get into your car. The car and the phone detect each other, share the resources, have a unified view. So you have like based on your patterns, the system decides, okay, I can switch over to the dashboard camera and even the audio of the car to like have an way of like keep on the conversations but driving safely on the other hand. So the same again, you're leaving the car, you're switching back home to your mobile because the resources of your car vanish, and then you go back and go in your kitchen, want to prepare dinner, and then it switches over to the other things. So this is all things you could do manually, right? Maybe not all of them, but at least these things is very hard to do with different ecosystems and different applications on different devices and so on to make it true. And if you would have the capability of see all of these in just a unified view, that would make things a lot easier. I mean, there's a plethora of resources available, but it's very hard to make good use of it. So let's go a bit more into the meat of all of this, right? So in the architecture, I already mentioned before, we designed this as a middleware. Right now, we are putting it on top of Oniro. None of the dependencies we are having currently is like depending on specific Oniro bits or something. So we also can do the development on just a normal Linux laptop or something. So this is not really a key point, but we are designing it in a way that it works with Oniro. We are testing it with Oniro. So if you run it on something else, you need to make sure that it keeps working for you. We are offering services and APIs to the applications to make use of the service of these resources that are available and how to use them. And every device that is part of this network has what we call a local agent that is like making sure that it has all the layers implemented and it talks to all the other devices around it. And then based on this local agent, we form the unified pool of resources. That is what we also call virtual resource devices, or sometimes even super devices, which is not the greatest term, but that's how we used it. And they together form like these local agents, form the local agents, sorry. So going a bit more into the different layers of the middleware we are designing here. So we have like going from the bottom up, we have the communication layer, then we have the virtualization layer, then we are envisioning an application management layer, which we are not touching right now. I come to that in a minute. And then we have on top of all of that, the intelligent coordination layer. All of these are forming the local agent. As of the current status, what we have implemented and running is the communication layer and the virtualization layer. The intelligent part is actually what is currently, as I'm speaking, under research as well as testing out various approaches to that. So this is like what we are looking in right now. The application management layer is something we put aside for a while. This is mostly targeted to having a way of like remotely executing applications, making use of the resources. But that again is bound a little bit to the general purpose use of resources like CPU, memory, and so on, as I mentioned before. We put that aside because we felt it was too complex to tackle that from the beginning. So, but it's still in there. Okay, so drilling further down, we start with the communication layer. So what we did there. We set out and looked at various protocols we wanted to, or we could use there, and we basically decided to at least look at 3 of them and figure out if they are fitting our use cases. So we looked at MQTT, we looked at Zeno, we looked at CoAP. So one important part for us was that there is actually an implementation already, an open source implementation we could use, because we didn't want to start afresh with a new protocol or implementing that all on our own. And all of these things also need to be available on Linux as well as Sapphire. We wanted to have device as well as resource discovery, most likely built into the protocol, so we don't have to like develop anything on top of that. And as I mentioned before, we want to have constraint devices in mind. Constraint is a very generic term, I know that, so we wanted to make sure that we have like a good use of small frame sizes. So if you run on low power, low wireless communication, we want to make sure that that is working. We want to have latency in mind, so having if we could, we wanted to avoid things like having TCP handshakes and so on, going back and forth. But really, that depends. In normal cases where you have like a Wi-Fi connection between devices, that doesn't matter at all. But if you go down and really drill down and you have like a mesh network with a few hundred devices and then you're losing a frame or something, that could be really annoying for the latency. And then obviously things like memory footprint and all the other things. So these have been like the attributes we have been looking when selecting. And in the end, we settled for CoAP. We tested out Zeno on Sapphire as well. We tested out on Linux, MQTT as well. But in the end, we settled for CoAP. That mostly comes because we also make use of the resource directory. I come to that later. But that was one of the main purposes we're having. And also we have been very happy about like how it handles like the low latency and frame size issues we're having. So keep in mind, this CoAP is for like the machine-to-machine communication. So if I talk about the use case with like the different video calls and so on, that's definitely not going over CoAP, right? That's would be a different protocol, but the coordination of all these streams and so on would happen over CoAP. So we're using the libcoap implementation on Linux and the native CoAP implementation on Sapphire. So we have support for IP version 4 and IP version 6. And we have it running in our testbed, or the way we are testing it on low power wireless communication. In our case, that is a thread mesh network we're using it for. And we have the resource directory implementation on Linux, which is a core part we will use in the next layer, in the virtualization layer, how we are actually getting all the resources, how we are putting them together, how we make them available to the upper layers, how they can use them, and so on. The resource directory implementation is only on Linux right now. We have been thinking about putting it on Sapphire. Code-wise, that is not really a problem to do. It's more like if you have a big network and it's growing, then you might not want to store all this data on a small sensor node or something like that. But it could be done depending on use cases and needs. So going one step up, we have the virtualization layer, which is basically, in our case, is the resource directory implementation, because it turned out when we did that, it was well fitted for at least for an initial resource abstraction. This might need to change later on. We are, as I said, we are very much work in progress, so nothing of this is fixed or anything, but right now, for us, it seems that it's fitting the bill quite well for us. So what is happening there is that the device joins the network. It announces itself to the multicast address, and if it finds a resource directory, it registers its own resources there. If it doesn't find one, and it's running on Linux, it will start itself and elevate itself to the available resource directory in the network. Yeah, so this is the resources I said about that. And then we have an API for the upper layers to query various ways of like these type of resources. It could be device types, it could be attributes, it could be the URIs of the devices and the resources. So this is like an API we're building on top of that. So if we ever wanted to change away from Corp, we could do that. So that's possible. And this is basically our first implementation of the unified view on the resources, which I mentioned in the first slides. So in these results we're having here, that can be used for the decision-making process later on that comes with the orchestration. So as I mentioned before, the intelligent coordination layer, that is our current focus. That is where our professors and my colleagues are actually working on and trying out different things here. So one of the things we want to have is using ontologies and schemas to express the attributes that these resources are having. We are looking into various things that are available for that. So we're looking at OCF, we are looking at the robotics ROS, we are looking at web things. So there are all different ways of like expressing these, and right now we are in the process of deciding what we want to go there. And we want to use these ontologies to find the best execution environment. So what that means is if we have something coming from upwards from the application or from the user, they want to dim a light, they want to like reduce something, they want to switch a video, they have a video call or something. And based on the ontologies and schemas we have available, all the information, then we can make the decisions based on that. And that, as I said, in the beginning, that could be a simple rule-based engine, or it could go further than that and learn from the pattern you're having, learn that you always take the last call on your car or whatever, right? So that is like things that can be built together there. And on the coordination approaches, we are having like, at the moment, we have a centralized approach. As I mentioned before, in the virtualization layer, if there's no other resource directory available, the device will make itself a resource directory and then use all the other ones. This is like obviously not very fault tolerant. So we are looking also into having at least a standby coordinator that will take over if the first one fails for whatever reason, like power out or leaving the network or whatever. But we're also looking, but that is not on the agenda for this year, maybe end of next year or something, into a peer-to-peer coordination. No central coordinator, but that is again very complex. And the way we are handling this project is that while on the one hand we are trying to do research and like working with academic, we also want to have like a working implementation going forward, and we want to like have the option to use at least parts of it. And yes, using parts of it is actually what we're doing already. So on Oniro, we have this concept of having blueprints. We want to deliver something that could be productized if people wanted to. We wanted to deliver something like to 60, 70% of readiness where you can take it, all the base components, the baseline, and then add your own stuff on top of it. So that's a generic concept we have in Oniro. So we have like various blueprints. And a few of them we have now started to incorporate parts of the ADI layers we're having. So mostly like communication and virtualization. So one demo we will show, we didn't have it here because we didn't have all the hardware here, but next month we will, at a conference in Italy, we will show a use case where we have a door lock, which is running on the Zephyr side. So it's a small RTOS-based system. You have the door lock connected to that. This one is connecting over the thread network or mesh network to a Linux gateway, which then over Wi-Fi connects to another Linux machine, which is a touch controller. And so in this case, what we are doing is like we are showcasing like the usage on Linux, the usage on Zephyr. We are showcasing that we can work as well on Wi-Fi, so really common networks, but also on low power and lossy networks. So that is also working. And the decision here is that the touchscreen controller can make based on the available resources. So whenever it figures out that there is the door lock available right now, then it can switch the UX dynamically. So this touch controller blueprint we are calling CATS, which is a context-aware touchscreen. So that means like it figures out, oh, there's a door like available, so I have another screen you can switch over to, like to enter your digits to open the door or something like that. So this is like a setup mix of hardware and software and various blueprints we're having together, and then also showcasing some initial work of what we are doing with Ellie. So this is like one part of it. But yeah, there's more to come. I mentioned that before. So for next year, so right now we are already looking and starting to look into the ontologies and schemas. I expect only results going really from getting the feedback from our professors on that, and then go to really implementing stuff, mostly like in the beginning of next year. And based on that, we finally can go to the stages where we think about how we want to handle the orchestration, what kind of technologies we want to use there. We very much want to keep that local. So for privacy reasons, we don't want to move all this data into a cloud service or something. That could be something someone else can add on top of that. We are not against it, but in the context of Oniro and for the blueprints and the use case we would love to have that all like on the edge, basically, the decision-making process. And yeah, that is also something we are looking into right now. And as I also mentioned before, we want to explore different coordination approaches, like going from central to at least failover standby and then to peer-to-peer. So this is a little bit of an overview of what we're having. And that's actually already the end of my presentation. So I would love to have questions, comments, flame wars, whatever. Go ahead.
You talked about latency. What latency do you have in mind?
So the latency I mentioned here was more on the communication part. So as I mentioned, so if you have a lossy network, like a mesh network, then you have like, if you have to hop, whatever, like 5 or 6 hops between the gateway and your end node, maybe. Then you have like a TCP handshake, as an example, right? You go ahead, you have like a 3-way handshake, and if there's a frame lost in between or something, that would have to restart all over again. So one of the attributes that we found interesting with co-op was that you can go with something like DTLS, where you have like you go ahead and send the message out. Everything is like in one frame. That's working well for us. So that is like the latency parts. Obviously, that also goes up if you go up the stack, but that's not something. So I mentioned that in the communication part. So that's something different. So that's what we mostly looked at, right?
So the latency is for getting the service to know, so registering to the same registry directory.
Yeah. So basically optimization on the communication level. So.
But just while handshaking. So.
Yeah, handshake would be one part. As I said, so if you select a protocol that is like very heavy and you have to, so one example. So these thread, they have a maximum transfer unit from 127 bytes. So that means if you have like a big packet, you already have to do like a package reassemble and so on. And if you miss like one frame in the packet, then you have to retransmit it all over again. So that is like the things. It sounds strange sometimes to optimize for that, but given in mind that we have like constrained devices, one of our customers in the design, we wanted to make sure that we have that. So and Corp is working well on the other protocols as well, but as I mentioned, it's only for the M2M part. If you want to stream or anything like that, you would switch to different protocols and only have like the coordination of that. Okay, thank you. Go ahead.
What's about the security authorization to access the device, and if you can elaborate more about privacy?
Okay, so the security part, it's easy, but not what you want to hear. It's we only have like the transport security in place right now. So there's no, from the architecture, we are okay to plug in the security, but we don't have added that at the moment. So that's not there. So that's definitely something that needs to be done. And on the privacy part, what we are focusing on right now is like we, besides the security that we need, is that we want to try to have most of the things at least in a local area, all the decision making. So if we can avoid it, we don't want to transmit it to like some big cloud service and do the AI crunching there, but instead we want to do the decision making and the part on the edge. So if you have like a bit more beefy edge router in your home or do it on your phone or something. So the architecture is flexible enough to have like the coordinator sitting in any of these components. So that would not happen on your Windows sensor or something like that, but it would stay in the same network. So that's like the privacy point we try to address. Yeah, but security-wise, as I mentioned, that is something that really much did a lot of work. Go ahead.
Julien from EclipseCon computer. So what was missing in EclipseCon with regard to QA when you made your evaluation?
So we tried it out, and most of the things have been working fine for us. So one of the things that have been not so well for us was like how we could run it on Sapphire. So making sure that we have the full integration with the rest of the networking stack, for example, so we can then use it like if you do the business logic in a Sapphire application, we want to use the APIs for that with POSIX and so on. So that is like one of the parts. For example, we are sharing some code between Linux and Sapphire, which are using the POSIX socket APIs and so on. And so that would need like more tighter integration into that for our use case, right? And then we haven't really been sure how we could build the same setup we have for the resource directory with Zeno in that regard. That might be a misunderstanding or not well understood from our side, but it was very well fitted for us when we looked at the co-op resource directory RFC. It was very much in our head working well. So that is, I mean, we can talk about that a bit later, about details on that. So we have, as I said, I mentioned that to you before, we have that still in our repositories. So there might be a way to switch over, but it might just be that we haven't been familiar enough with that. So. Okay, sure. Any more questions, comments? Go ahead.
Maybe about the resource consumption, what you need for the coordinator. Measurements already done?
No, we don't have measurements. So as I said, we run that on Linux. I think we had a test trial to do the implementation on Sapphire as well. So that is not the problem. It's more like if you run into like a big network where you have like a lot of resources, you need to store that somehow. You have like the memory consumption of all of these. That is like what we avoid about if the small devices are not capable for that. But in the end, you don't want to. Okay, so depending on the device type you're having and the power budget you're having for these, it's also like wise to like keep them sleeping as much as possible. So if this kind of device running on a battery, for example, would act as a coordinator, it would have to wake up way too often and like have a steady connection and making sure that it's listening on the multicast address all the time. So this is like one of the designs where he said it would be best if the device is like main powered, if possible, but if you don't have that, so then it would at least switch to a device that has enough battery power, like a phone or something like that. So that is the idea here. So. Okay, so if there are no more questions, thanks for your attention, and have a good rest of the day, and a good trip home. Thank you.